as part of the paid program, one of the things we've been doing is developing tools to assist in task mapping on blue waters. So that's what I'm going to cover on my tutorial. So basically what I wanted to cover, I don't know if I'm going to have enough time, is basically why task mapping is important on blue waters. Try to know when to do it and how to do it. And then I'm going to show some examples based on the MILC application and Qbox. So we've been getting really good speed ups with those. So yeah, and my main focus is going to be on the automatic tools we've been developing. So basically, these tools work with any MPI application. They don't require any modification of the source code, and they're very easy to use. So first question, what is topology-aware task placement? So simply the idea is, so like Jeremy said, the topology-aware scheduler gives us compact allocations, but then the question is, inside your job allocation, how do you place the MPI tasks so that the communication between nodes is minimized and you minimize link contention? So this is not the same as simple rank reordering. So you require knowing during your job where the MPI tasks are and what's the distance between the tasks. So, and the question, why is this important? It's basically because on blue waters, you can get, if the tasks are not placed properly, you can get a lot of link contention, and this can slow down the application. Depending on the application, it can slow down a lot. So you can get, with good topology mapping, you can get improvements of more than 2 times X in very large jobs on some applications. So first off, I'm just going to show a very simple example of why topology mapping is important. So you can extend this to n dimensions. And the same applies. So basically, assume we have like a 2D application grid where the cells, which are MPI tasks, communicate with their 4 nearest neighbors. And then you have a 2D torus, and you want to map this grid to the torus. So if the shape is the same, then obviously you want to preserve the structure so that each task only sends to the node which are nearby. So you only have links. Each task only uses 4 links for communication, right? Now, what happens if we do a random placement? So the placement is completely random. You're going to have longer paths, which means that for the same communication, you're using more links. And this can produce link contention, and ultimately, the application will take longer to execute. So this is a simulation result of what happens if you map a 2D 10 by 10 virtual grid to a 2D 10 by 10 torus. So assume we have near neighbor communication like I showed in the previous slides, and each task sends a unit of communication to each of its neighbors. So, and I'm assuming that since you can have multiple shortest paths between tasks, you're selecting one of those at random. So if you use the row order in this case to preserve the structure, you have that the max link load is 1, which is awesome. And if you do a random placement, it's much higher, right? So this means you're getting links which could potentially be bottlenecks and slow down the application. So but what happens if you map the same grid to a shape that is 5 by 10? So in blue waters, your shapes can be different. You're getting slabs, but they could be long or flat or whatever, right? So if you do the same row order right now, you get a solution which is almost as bad as random placement. But if you do a near optimal mapping, and well, here I say near optimal because this was obtained with a heuristic algorithm, then you can get much better link load. So are there any questions up there?
Hi, just wondering if you could give a quick definition of what link load is measuring?
Yeah, in this case, it's simply, so if you're sending like a unit of communication, it's how many of those units are passing through a link. Which, in the real case in blue waters, would be bytes or bytes per second. Okay, so some of you may be wondering, so what does, oh, question?
Is it possible that in an actual case, the Cray hardware would recognize that some link is overloaded and change the routing?
No, I don't have the answer to that question. I don't know how the routing works, so.
No, there's no dynamic routing on the system.
Okay. Okay, so some of you may be wondering, so what kind of mapping does Blue Waters do if I don't do anything about it? So basically what happens is you have your tasks in rank order, and then you have, the Blue Waters has a node list, which I think it's obtained with a space filling curve. I don't know exactly the properties of this list, so maybe it's possible that two nodes that are closest in this list are close in the topology, I'm not sure. But anyway, it's just a direct mapping of the task by rank order to the processors. So with this, there's no real guarantee that tasks that communicate are going to be close by, because it depends on the order here, and there's no actual guarantee that tasks that communicate are, for example, if this one is communicating with this one, that these two nodes are going to be close. So it can depend on the shape. So there's no real guarantee. So one solution, at least with the shape issue, is you could, if you're getting bad mapping with some shapes, then you can run on shapes that you know are good. But the problem with this is, well, the problem is how do you know what shape to use? You could do it by trial and error. And another problem is if you're requesting a specific shape, then the scheduler could take much longer to launch the job, because you need to wait until that shape is available. So I don't know if someone here do you request specific geometries when you launch your applications? I know that MILC does that, but I don't know if someone else. Does someone here actually use mapping in their applications? Okay, that's what I expected. Okay, so another question is how important is my mapping on my application? So this is not there's not a clear answer for this. So it depends on your communication patterns, on how much communication you're actually doing, on your computation to communication ratio, on the shape that your job is getting, and on the job size. So it may matter, it may not matter. So there are applications on which on very large jobs can get a really good speed up. So yeah, the question is, how do I know when to do mapping? So probably the easiest solution for users would be simply to use an automatic tool and see if there's an actual improvement. In the worst case, there's no improvement. Or you could also, if you know the properties of your application, you could know. So if you know there's going to be a high communication ratio compared to computation, well, then you probably should look at mapping. And another solution is if you don't have this information, is to use profiling tools to try to figure it out. So right now, I'm going to mention quickly some profiling tools. So this is a list of some of the popular ones. So you have Qbox, which is a large suite, which gives you MPI timings and things like that. And there's also an MPI, which is a more easy. You just compile a library and link it with your application, so you don't need to instrument your application. But these two didn't really work for us. They didn't have what we need, so we developed our own, which is Topo Profiler. It's also a link time library, so just link it with your application. And basically what we wanted was more topological information, so we wanted to see the actual hop bytes between tasks and the ability to extract the communication graph. So using the Topo Profiler is just a matter of building the library, link with your application, then you get some output files after the application runs. So this is output you get. So I've underlined the interesting things. So basically, this gives you the total execution time of your application, and then you can see things like the average hop bytes, which is calculated as, so the hop bytes of one task is the sum of hops to its neighbors multiplied by the amount of bytes going to its neighbors divided by the total amount of bytes. So that gives you like an indication of how close a rank is to other ranks during that job run. And it tells you also how much time was spent doing communication. So you can get a measure of what's the actual ratio of communication time to the total run time. And it also divides by the point-to-point communication and collectives. And other things that it tells you is where each rank was placed in the machine. These are the 3D coordinates in the machine. And you also get a lot of information on collectives, like the timings. And recently we've been toying with the option to also see the hop bytes of collective operations.
Is that where it's actually behind a barrier? Oh, I'm sorry.
Question, so how do you define idle time in that graph?
Yeah, we should probably rephrase this. It's communication time. It's this time spent on communication. So yeah, this tool can give you an idea of what's happening from the communication point of view. So now the question is, okay, if you want to do mapping, how do you do it? So of course you can do the application, but that's hard. The application developers need to know how to do it. There are ways to access topological information. We have our own library called Topo Manager to do that. Other ways to do mapping include using the grid order tool in the CRAPAT, or using Topo-Aware, which I'll briefly describe. And then we have our own mapping tool, which we call, it's a general mapping tool, so I'm gonna talk more about that. So CRAPAT has grid order. So it basically tries, when you profile the application, you run it, it tries to detect the communication pattern. If it detects a grid pattern, then it calculates a rank order. But it does this outside the job, so it really doesn't use topology information. So it doesn't have any way of explicitly placing communicating nodes nearby, and doesn't deal with irregular patterns. And then there's Topo-Aware, which this gives us very good results with MILC. I know it's being used in production runs. So this was developed by Robert Fiedler from Cray. And well, the limitation we saw with this tool is that you basically have to know what your application grid, how it's partitioned. You have to tell Topo-Aware that. And then it'll tell you what shapes you need to run the job. So it's restricted to running on those shapes. And yeah, it only works for, it assumes near neighbor communication patterns, which might not always be. So our tool, well, I'm not gonna go into much detail. So basically what it tries to do is, given the communication graph, which we obtain with the Topo profiling tool, it tries to minimize hop bytes, which for each rank is the sum of the bytes to its neighbors multiplied by the distance to that neighbor. So it'll basically try to keep the tasks close by. So this metric doesn't necessarily correlate, of course, with execution time, but we've seen that in most cases it gives good results. And we also favor solutions which have smaller max hop bytes, so that there could be ranks. Even though the average could be small, there could be some ranks which are far away to their neighbors, and that could be a source of imbalance. And we also give more weight to the hop bytes in the Y direction, because I don't know if you're aware, the Y links in Blue Waters have bandwidth as the other links. So we take all these things into account, and we implement an algorithm. So the problem of minimizing this is NP hard. So we have an heuristic algorithm. It does multiple trials, and we compare with several other algorithms. So this problem is not new, but there's many algorithms to solve it, but they're either too slow, because these problems are huge. You have so many thousand tasks. Or they're either too slow, or they find bad solutions. So this is how we run our tool. So basically, it's very simple. So you do this inside your job. So we assume you have already profiled the application. You got the communication graph file. So inside your batch job, you first run the mapping tool, giving it the communication graph. And then you just export this variable, and you run your application, and that's all. So the good thing with this is that it runs on any geometry. It supports arbitrary topology, so it supports, even if they're on Blue Waters, you have service nodes, so it can work with that. And a nice thing is that we run the mapping on all processors. So this is basically for two reasons. It allows increasing the search space. So each subset of processors search a different solution space. And it also, with very large problems, the algorithms become slower and slower, so it can do less and less trials. But since we have more processors, then we can just use them to compensate for that. So are there questions? Okay, so now I'm going to go through some examples of what results we've seen. And so the methodology we're going to follow for this is basically to profile, so you see how it behaves, and then to apply the automatic task mapping to see what we get. So first we start with the MILC application. So it has a 4D lattice, and this is an application which is extremely sensitive to placement, and it has a near neighbor communication pattern. So these are the results with the Topo profiler. So this is with 16,000 task runs. So for example, on an 8x8x8 shape, you get this. So total execution time is more than 5 minutes, and there's like approximately 40% time spent on communication, and most of this is from point-to-point MPI send and receives. And then the curious thing is you go to a different shape, but it's exactly the same job. And now you have you have 63% time on communication, which is still on point-to-point send. So yeah, something is definitely going on here. And the hop bytes, if you've seen, the hop bytes have increased. So the tasks are farther away than their neighbors than they're supposed to be compared to this one. So what do we get if we apply mapping? So what we got, this is for 8,000 ranks. So we compare also with the Topo-Aware tool. So Topo-Aware only runs on this specific shape. It doesn't run on these shapes. So we got a very good performance, and which seems to be very robust to the shape. So it's similar, regardless of the shape you run it. And as we can see, the default mapping on Blue Water sometimes performs badly. And if you go to larger and larger jobs, then the situation gets worse. So with 16,000 tasks, the default, for example, in this shape, performs really badly. And if you keep going to larger jobs, it can be even 2 or 3 times worse. Are there questions? Okay. So this is going to be my last example. So this is Qbox, which is an MD code developed at Livermore. It was a Gordon Bell Prize, 2006. So the communication of this application basically has it does dense linear algebra, and then it does 3D FFT. So this is a different communication pattern. What it does, the 3D FFT's work is basically the states are divided across columns in a 2D process grid, and each of these columns is doing several MPI L2Ls. And then this information is aggregating the densities with an MPI all reduced on the rows. So we profiled this to see what was happening, and we saw, so it has, I think this is for a 16,000 tasks job. So it spends 35% of the time in communication, which is not too bad. And almost all of this time is on collectives, right? So, and then we further analyzed those collectives, and we saw that most was due to the MPI L2L. This is for one particular example, so there were like 84 groups of size 256. spending more than 20 seconds on collectors, and most of this was by the MPI as well. So of course, a strategy would be to these subgroups cluster the MPI tasks together. We just let the automatic tool do it. And these are the results. So these are very recent, so I haven't been able to collect a lot of them, but these are the results we got for. So for example, on an 8,000 task job, depending on the shape, the performance is very similar to default mapping, but on some shapes, this one, for example, was 12% better in execution time. And going to a larger job on this particular shape, we got like a 57% speed up due to the optimizing of the all-to-all placement. So yeah, there's room for improvement when you do mapping, and it kind of depends on the application and the shapes. But yeah, it's definitely something worth a try. So thanks. And just mention that these tools are freely available if anyone is interested. We're still adding features and polishing, but I mean, anyone interested, just contact me.